Okay, today's topic is limit of a function. Sometimes when we are using the function y equal to fx, we are interested or frequently finding the value of function some x equal to c near but not actually on that point of fx. This situation occurs when we are using irrational number such as root 2 or pi. For calculation purpose, we use near rational values. Another situation occurs when a free falling particle, we finding out its speed near the earth's surface, not actually on the earth's surface. And some other many more situation occurs where the near value is very important. Consider a function f of x equal to x square minus 1 by sorry x square minus 1 by x minus 1. See, this function is not defined at x equal to 1. But what is the behavior of this function at x equal to 1? We can simplify this function as fx equal to x plus 1 into x minus 1 by x minus 1, that is equal to, as x not equal to 1, x plus 1, since x not equal to 1. Now what is the graph of this function? See the graph of the function. This is y-axis, this is x-axis. This is origin, this is y-axis. Okay. So suppose consider this point is minus 1 and this point is 1 approximately. So graph of this function should be like this. Okay. This is the graph of the function y equal to x plus 1. Consider this is the x equal to 1. And this is the value of the fx at x equal to 1. This point is y equal to 2. Now as function is not defined at x equal to 1, so we cannot find f of 1. But when x approach to 1 from any less than value of 1 or for any greater value of 1, we see that fx approach to 2 or y approach to 2, and this near value is the limit value of this function. This is the limit value that x approach to 1 from both sides, less than value of x equal to 1 or greater value of x equal to 1, then fx approach to 2, and we can say that this is the notation of the limit x tends to 1 f of x equal to 2. We read it limit, this is x tends to 1. That is when x approach to 1, fx approach to 2. If we use algebraically this function, then what we should get? See this table, x f of x equal to x square minus 1 by x plus 1. Suppose first we take the value near to 1. So 0.9. fx should be 1.9. Next 2 point fx is 1.1. Then fx should be 2.1. Next x is take any value 0.99, then fx is 1.99. Take in x is 1.01, then fx is 2.01. So consider x is 0.999, fx is 1.999, and another more value x is 2.001, fx is 2 point, sorry, x is 1.001, fx is 2.001. So from this table we definitely say that when x approach to 1 from some less value of 1 or greater value of 1, fx approach to 2. So this is the limiting value of fx at x equal to 1. Now come to the definition. Consider fx is a real valued function. Define any open interval which contains a real value c. But fx may or may not be defined at c. Then if x approach to c, fx approach to L, that is if fx approach to L when x approach to c, then we can say that limit x tends to c f of x equal to L. This is the informal definition of limit. Okay. Now think that limit of a function does not depend on the function at limit of a function at a point does not depend how the function is defined at that point. Consider the function, suppose number a, f of x equal to x square minus 1 by x minus 1. Suppose gx equal to x square minus 1 by x minus 1 when x not equal to 1 and equal to 1 when x equal to 1. And another function c hx equal to x plus 1. Now try to draw the graph of these three functions. What is the graph of function a? This is y-axis, this is x-axis, this is origin, consider this is minus 1, this is 1, this is also 1. So graph of this function should be, that function is not defined at x equal to 1. There should be a hole at that point. Okay. So this is 2, and we already got this function that limit x tends to 1 fx equal to 2, and you see that this function is not defined at x equal to 1, but we got the limit value. Okay, Next, see the question number B. Try to find the graph of function B, uh, equation B. So same thing, this is y-axis. Okay, move to next page. Try to draw the graph of function P. So this is y-axis, this is x-axis, and this is x date. Suppose this is -1, same thing, this is 1, this is 2, and this is 1. So graph of this function should be like this. And there should be a hole at x equal to 1, but because the function is not defined at x equal to 1, and when see the definition, when x equal to 1, when x equal to 1, f of x equal to 1. So when x equal to 1, f of x equal to 1, this is the functional value. So for this function, limit x tends to 1, gx equal to 2, but g of 1 equal to 1. So this function limit value and functional values are different. Next come to the function c. What is given? hx equal to x plus 1. Try to draw the graph of this function. This is the origin, this is x-axis, this is y-axis, this is x dash, this is y dash, and this is -1, 1, 2, also 1. Now the graph of this function should be like this. Now see this function when x equal to 1, hx equal to 2, and this limit value also, limit x tends to 1, hx equal to 2, also h of 1 equal to 2. This function also limit value and functional value same. So we got three different function. For function a, that limit functional value at that point does not exist, but limit also exists. Function b, limit exists, but limit value and functional value are different. And function c, limit exists and limit value, functional value are the same. So what we got, the limit of a function does not depend how the function defined at that point. Next come to the two functions. One is identity function. Identity function. So as we know, for that identity function is f of x equal to x. Let c be a point or real number. So try to draw the graph of this function. This is origin, x-axis, and this is y-axis. This is x test. So the graph of this function should be, as we know, this 45-degree angle, fx equal to x or y equal to x. So C is a point. Suppose this is the C, x equal to C. So this is y must be C, this point. So from the graph we can say that limit x tends to C, f of x equal to C. So for identity function, limit of a value is the same functional value. For identity function, limit of any value x tends to C is the C. So limit of, if it is 2, then f of limit x tends to 2, f of x equal to 2. So we got the limit of identity function. Next is constant function. Next function is constant function. As we know, constant function is fx equal to c, where c is any real number. Now try to draw the graph of this function. This is origin, this is x test and x, this is y0, y test. So this function should be fx equal to c. Suppose this is the c distance. This is the limit of c. And this is the length of c. So this function always parallel to x-axis. So for any point of any point c, it is always c. Same. Limit x tends to, suppose k is any real number. Then we can say that limit x tends to k, f of x equal to c. Such as any constant function, limit x tends to 3. 4 is the constant function. It is equal to 4. So we got the limit of identity function and constant function. Now there are some limit laws. Next, limit laws or algebra of limits. Let first consider L, M, C, K are real numbers. Then number 1. Number 1, first consider limit x tends to c, f of x equal to L, limit x tends to c, g of x equal to m. Then number 1, limit x tends to c, f of x plus g of x equal to L plus m. Number 2, limit x tends to c, f of x minus g of x equal to L minus m. Number 3, limit x tends to c, k into fx equal to k into L. Number 4, limit x tends to c, fx into gx equal to L m. Next, limit x tends to c, fx by gx equal to L by m, provided m not equal to 0. Number 6, limit x tends to c f of x to the power n equal to L to the power n, where n is positive integer or n is natural number. So these are the limit laws. So limit of a sum of two function, subtraction of two function, multiplication of two function, constant multiplication of a function, and quotient of two function, we got the limit laws. There are so many others limit laws are there. So up to now what we got, that limit is an approach of a function from both sides, and a function limit of a function does not define how the function is depend on that point, and function may or may not be defined at that point. See another more example. Consider f of x equal to root of x minus 2. See here, the function is defined at x equal to 2 and f of 2 equal to 0. But function is not defined any less value of 2. Therefore, limit of this function at x equal to 2 does not exist. So we can write here limit x tends to 2 f of x does not exist. Does not exist because for this function x minus 2 always greater than equal to 0, that is x greater than equal to 2. So function is not defined any less value of 2, may or may not define, but must be defined some less value of that point, some greater than value of that point. Then we can say limit exists and then we can evaluate the limit. But here limit does not exist. Okay, up to now this today's class. Next class we will discuss more about limits.